In this video, I am going to explain oscillations and waves which comes under module 1 of engineering physics prescribed by VTU. Here I am going to explain the following points, that is simple harmonic motion, differential equations of simple harmonic motion, mechanical simple harmonic oscillator. I am going to explain simple harmonic motion. A mass is said to be performing simple harmonic motion when the restoring force is proportional to negative of the displacement. That is, F is proportional to minus of displacement. So when we remove the proportionality, a constant will come into picture. So F is equal to minus K into X. Here K is a proportionality constant, also known as spring constant or force constant. So the force constant represents the amount of restoring force produced per unit elongation and is a relative measure of stiffness of the material. So again we can write F or restoring force is equal to minus K into X, and as according to Newton's law, the force can be written as mass into acceleration. So m into d square x by dt square is equal to minus kx. So if we divide this equation throughout by m, then we can arrive at one more equation. So if we consider omega naught square is equal to k by m, then the above equation takes the form d square x by dt square plus omega naught square into x is equal to 0. Here omega naught is called angular velocity, which is equal to 2 pi f, and f is the natural frequency given by 1 by 2 pi into square root of k by m. Next, I am going to explain mechanical simple harmonic oscillator. So if we consider a mechanical spring which resists compression or elongation and it is an elastic material, at the lower end of the spring a body of mass m is attached. Mass of spring is neglected here. When the body is pulled down by a certain distance, say x, and when it is released, it will undergo simple harmonic motion. When there are no external forces acting upon the body, the oscillations are said to be free oscillations. The mass oscillates with its natural frequency here. The motion of mass m attached to the spring follows a linear differential equation. That is, restoring force F is equal to minus k into x. So according to Newton's second law, the equation of motion can be written as d square x by dt square plus kx is equal to 0. So this equation is considered as second order homogeneous linear differential equation. And further, the auxiliary equation is d square plus omega square into x is equal to 0. So here the value of d is plus I omega and the value of d is minus I omega. Next, the general solution is given by, that is that for the displacement x is equal to a into e to the power of I omega t plus b into e to the power of minus I omega t. That is equal to a into cos omega t plus I sin omega t plus b into cos omega t minus I sin omega t. So this is the expanded formats, whatever when we expand e to the power of I omega t or e to the power of minus I omega t. On simplification, we get the another term, that is a plus b into cos omega t plus I into a minus b into sin omega t. Further, in place of a plus b, if you consider c, and in place of a minus b, if you consider d, the further equation can be written as c into cos omega t plus d sin omega t. So it may also be expressed as x is equal to a cos omega t minus phi. So here the value of phi is equal to tan inverse d by c, and the value of a is equal to square root of c square plus d square. And in the next slide, I am going to show you the picture of the spring and the mass m attached to it at the other end, and the mass is displaced by a distance x because of the acceleration due to gravity. And here is a chart showing the displacement of the object, velocity, and also acceleration of the object with respect to time. In the next slide, I am going to give you the information about velocity of the particle given by Vmax is equal to dx by dt, that is equal to minus omega into a, and the acceleration of the particle is equal to dv by dt, that is equal to minus omega square into x. The angular velocity omega is equal to square root of k by m, and the period of oscillation, that is capital T, is equal to 2 pi into square root of m by k, and the phase of the wave is given by omega into t. And further, the natural frequency is equal to 1 by 2 pi into square root of k by m. So these were all the supporting equations for expressing the equations of simple harmonic motion. So thank you.